Hello, in this video I'd like to talk about a fun way to think about matrices, and that's in terms of basis matrices. So hopefully you're familiar with the basis vectors. Usually we call these E sub I for various values of I. We have a vector that is all zeros except for a 1 in the ith row, and somewhere along the lines you have to specify the dimension of these things, but you should do that separately. Or you can just kind of take the natural embedding of R1 into R2 into R3 into R4, and it just goes along with these very nicely. So you don't have to worry about you don't have to worry about the dimensionality of things. Similarly, we can define a basis for the matrices as a vector space. Again, fix a dimension, or you can kind of do a dimension embedding sort of thing. And these, I want to denote these as M sub ij. And these matrices are going to be all zeros except for a 1 in the ith row and the jth column. And so these, just like these vectors, form a basis of Rn. These vectors form a basis of the space of appropriately sized matrices. And I find this a really useful way to think about matrices in terms of remembering how to do matrix multiplication. For the longest time, I had trouble remembering which one was the rows and which one was the columns when doing matrix multiplication. So before I show you that, let me define a little bit of notation here. I know that I write M sub ij to indicate the ijth basis matrix, but I'm also going to write A sub ij to indicate the entry of A in the ith row and the jth column. So if you wanted to, you could actually write the entry of Mij in the ith row and jth column. Well, I guess we should use different variables. In the kth row and elf column is going to be, well, it's going to be 1 if I is equal to k and j is equal to L, and it's going to be equal to 0 otherwise. So that's one way that you could define these matrices. So if you want to multiply these, there's two simple formulas that you need to know, and that's it. So if I want to multiply a basis matrix by a basis vector, if the adjacent indices agree, then it's just going to be the remaining index basis vector of the appropriate dimensionality. And if not, it's going to be the 0 vector. So this way we can, and then by using distributivity, we can extend this to define how to multiply any matrix by any vector of appropriate dimensions. And then if we want to multiply two basis matrices together, again, it's going to be almost the same thing. It's going to be the remaining indices, assuming that the adjacent indices agree with each other, and it's going to be the 0 matrix of appropriate size otherwise. And just knowing these two rules is enough to do all matrix multiplications. Let me show you an example. Suppose I want to multiply this matrix by this matrix here. Well, what this is So this matrix here, we can write as M11, so that gives us this one here. And then we need to add in 2 times M13. M13 is going to be all zeros here except for a 1 here. And then we multiply by 2 to get a 2 here and zeros everywhere else. And then we add it to everything else to change this entry. And then we'll have, this corresponds to this entry. And then we'll have something corresponding to this entry. So we can write this matrix here like this, and then we can write this vector here. This is just going to be E2 minus E3. And we can solve this just by distributing. Normally I would skip all of the terms in the distributivity that wind up being equal to 0, but I want to show you this in full so that you understand what's going on. So we do M11 times E2. That term is going to be 0, but we'll get rid of it later. We have 2 M13 times E2. Again, that's going to be 0. And then we have 3 M22 times E2. And then we have minus M11 times E3 minus 2 M13 times E3 minus 3 M22 times E3. And then we can just go through it, right? This is all we're doing is basic algebra, right? This is just distributivity. And then we can go through and we can, well, get rid of all of the terms that are 0. This one's 0. This one's 0, right? Because the adjacent indices don't agree with each other. This here is, these 2's agree with each other, so it's going to be this 2 that's left over. This term is also going to be 0. This term, there's adjacent 3's which are equal to each other, so it's just going to be the 1 that's left over. And then this term here is also 0. So we're left with 3e2 minus 2e1. In other words, this vector here. So in case you get confused about matrix multiplication, you can just do this to do any matrix multiplications. It works best with sparse matrices. If you have sparse matrices, it's actually the best way to think about this. If you have matrices with a lot of entries, maybe you want to be using a more traditional formula. But this is how I like to think about multiplying. You can do this with matrices times vectors or matrices times matrices. And in fact, you can do this for all sorts of things, right? This is, for instance, when defining the quaternions, it's very useful to define multiplication on the basis quaternions, right? 1, I, j, and k, and then just say, oh, well, everything distributes after that. And you can also use this to define, I really like using this to define the cross product. I know that there are other definitions of the vector cross product in R3, but I really like just specifying what the cross product is between each of the 3 basis vectors. You have some sort of very nice table, and then saying everything is just linear from that. This is how in higher level math, or at least in my experience, this is how I've seen a lot of things happen using linear algebra, where you define everything for the basis, and then you just use distributivity to extend, and maybe you have to prove some sort of well-definedness, or maybe it comes free. There's no worrying about duplication, duplicate cases, or multiple ways of doing the same case. So it's well defined. And This is how you can define tensor products, right? This is how I saw tensor products defined when I learned about them in a higher level math class. So it's a very useful way, and it reflects the way that mathematicians actually think about these things to define matrix multiplication. So I encourage you to consider teaching basis matrices as a way of thinking about linear algebra. In fact, if you wanted to, you could have a linear algebra course that didn't draw any matrices at all. It just wrote everything out like this. And then maybe presented matrices as a shorthand, matrices and vectors like this as a shorthand for these more fundamental notations happening underneath. And again, you can do all of linear algebra this way, and it's a very useful way of thinking about things. I also want to quickly show you the general formula for multiplying two matrices together and what that looks like when we're working with basis matrices. So any matrix A is going to be the sum over the appropriate I and j of the ijth entry of A times the basis matrix Mij. Right? This is kind of the definition of how entries of a matrix work. Right? The Aij is the coefficient when we write A in terms of this basis. And so if we wanted to multiply two matrices together, well, it would just look like this, right? We're expanding out A and B using this identity here. And then we can distribute, right? We can distribute this over this sum. Oops. And then we can distribute back. We can take each of these terms and distribute them into this sum. And shuffle things around a little bit. And then this term here is almost always, so this term here is almost always going to be equal to 0, right? Unless j is equal to k. So we can get rid of everything else from our sums except the case where j is equal to k, and we can write our sums like this. And then this product here, when j is equal to k, is going to be equal to the outer indices, right? M, I, L. And if we wanted to, we could write this as the sum okay. Yeah, I got rid of k. The sum over IL of the sum over j of A, ij, E, j, L times MIL. So what this is writing this product matrix in terms of the basis matrices. These are the coefficients, and we recognize this as the formula for the IELF entry of AB. So that's how you can work out from the notion of a basis matrix and from all of these ideas and in particular the formula for multiplying basis matrices, how you can then work out the more traditional formula for multiplying for the entries of the product of two matrices. And of course, the thing that actually works pretty well for me is to just remember this formula in terms of the J's being next to each other. And I find that very helpful. Uh, and then, of course, you have to remember which index is the rows and which index is the columns. But I think that this is a really useful way to present and to think about matrices. And so I'd encourage you to think about matrices in this way.